This is the third lecture from the series Making Sense of QFT. The title is Dirac's Interactions. Here is the outline. In our previous lecture, we were able to construct a full relativistic quantum description of a single elementary particle. Logically, the next step is to describe systems of many particles and interactions between them. Just as in the previous lecture, we will frame our discussion in terms of unitary representations of the Poincaré group. We will see that if particles do not interact, such a representation can be easily constructed. Dirac was first to classify different interacting representations in terms of so-called forms of dynamics. There are strong reasons to believe that Dirac's instant form of dynamics is prevalent in nature. Then I will talk briefly about several attempts to build instant form interaction in n-particle Hilbert spaces. In my opinion, these attempts were not very successful. The main reason is their inability to describe systems with variable number of particles. This will be the topic of my next lecture. Recall from our previous lecture that each particle is described by its own Hilbert space, which carries an unitary irreducible representation of the Poincaré group. Quantum mechanics tell us that an n-particle system has to be described in a Hilbert space H of n, which is the tensor product of one-particle spaces. I should have mentioned that if particles are of the same type, then product symmetrization should be involved for bosons and anti-symmetrization for fermions, but we will not spend our time on such details. The tensor product structure means that all observables of individual particles can be also found in H of n with their properties like spectra, commutators, etc. intact. And that all observables of different particles commute with each other. That's basically the definition of the tensor product, which seems physically reasonable. Now recall the main postulate of Wigner's relativistic theory. There must exist 10 Hermitian operators satisfying Poincaré commutators and representing 10 total observables: momentum, angular momentum, boost, and energy. So in order to move forward, we have to construct such operators. In the tensor product Hilbert space, we have one particle observables available to us. So it seems natural to seek expressions of the 10 generators as functions of these one particle observables. Later we'll come to the conclusion that this is not such a good idea. But let us now stick to it because we don't have any better suggestion at the moment. Here is one simple solution of this problem. We can construct generators as sums of single particle operators. Elementary calculation shows that thus defined generators, I will mark them by the subscript 0, they really satisfy all requirements. So they provide a full description of the n-particle system. And one can easily convince oneself that this construction corresponds to the absence of interaction between the particle. This is not so interesting. Naturally, in the same n-particle space, H of n, we can construct many different sets of generators. They will be different from the zero subscribed set. And here we arrive at our definition of what is the meaning of interaction. Interaction is the difference between true generators P, J, K, H from their non-interacting counterparts P0, J0, K0, H0. Only one interacting representation exists in nature. So our task is to choose somehow this unique set of generators from the infinite range of possibilities. Here I want to stress one important point. If we somehow manage to construct the 10 interacting generators, then we know everything about the physics of our n-particle system. Every question can be answered by applying some well-defined math. Here are some examples. The most important operator in quantum mechanics is the Hamiltonian. By diagonalizing the Hamiltonian, you can obtain the spectrum of energies and wave functions of bound states, if such bound states exist, of course. The knowledge of the Hamiltonian will allow us to calculate scattering processes that are encoded in the S matrix. Another important application is calculation of the time evolution of wave functions and observables. Here, as an example, I show how one calculates the time dependence of the momentum of the second particle. This expression includes commutators between P2 and the Hamiltonian. Since interacting Hamiltonian is a complicated function of particle observables, the commutators here are non-trivial, and the time dependence of the momentum P2 will depend on what other particles are doing. In other words, we'll have interaction. My last example is transformation of the first particle's x coordinate with respect to the boost in y direction. You can recall that the effect of boosts on the position is usually described by Lorentz transformations from special relativity. But here we have an opportunity to verify these formulas. I'm not going to dwell on this point here. We'll return to this idea in future lections. So let us now think how we can define interactions in the 10 Poincare generators. We can recall that in non-relativistic physics we introduced interaction in the Hamiltonian. We simply defined the so-called potential energy as a function of particle variables. Once this was done, we could calculate everything we need about our system. But in relativistic physics, things are not so simple. It's not difficult to show that adding interaction in the Hamiltonian only doesn't work. We know that in the Poincare algebra, the commutator of x component of momentum and boost is proportional to the Hamiltonian. But if our momentum and boost are the same as for free particles, then the Hamiltonian should have the non-interacting form as well. And this is a contradiction. This means that interaction terms should be present either in the momentum or in the boost or in both of them. In other words, in addition to the classical potential energy, we should consider potential momentum or potential boost. Paul Dirac was the first who noticed this peculiar property of relativistic mechanics. In his influential 1949 paper, he suggested a classification of different ways to introduce relativistic interaction. He called these ways forms of dynamics. We will discuss only two Dirac's forms of dynamics, point form and instant form. In the point form of dynamics, interaction operators are present in the Hamiltonian and in the total momentum. In the instant form, the interaction is present in the Hamiltonian and in the boost operator. Now we have to make a choice, which form of dynamics we are going to adopt for our studies. I will select the instant form simply because all our experience tells us that space translations are very simple transformations that do not involve interactions. It is true that so far we haven't noticed experimentally any interaction effects of boosts, but perhaps this is because we don't have much experience observing systems from a moving reference frame. Now we have to focus on constructing four interaction operators, the potential energy and three components of the potential boost. As I mentioned before, it looks reasonable to build these interactions as functions of one-particle operators. Recall that to maintain the relativistic invariance, the interaction potentials V and Z must satisfy a set of non-trivial commutation relations. So we are having a very complicated mathematical problem. There were some heroic attempts to solve this problem, and I would like to mention especially the works of Bakamian and Thomas in 1953 and Koester and Polizo in 1982. On one hand, these attempts were successful because all required conditions for interactions were satisfied. But on the other hand, this whole line of research looks rather unsatisfactory. The obtained solutions were mathematically very complex, but the most important defect was that these solutions were not applicable to systems with variable numbers of particles. And the last point is the most important. Indeed, in real life, we have a multitude of phenomena where the number of particles is not conserved. These are decays, nuclear reactions, emission and absorption of light. So it's not a good idea to limit ourselves to a fixed number of particles in the Hilbert space H of n. But then we have to work in a Hilbert space where all possible particle numbers can coexist and particles can be created and annihilated. This will be the topic of my next lecture. Thank you for your attention.